Good morning, all. I'm Dr. S. Suresh, Assistant Professor, St. Joseph College of Engineering. First, I welcome our pattern's respected chairman, Dr. B. Vamonaran, our Managing Director, Mrs. S. Jesipriya, Director, Mr. B. Shashishekar, Principal, Dr. Vadi Shashikar, Team Research, Dr. B. Arudardhani, and Head of the Department and Convener, Dr. V. N. Nandini. Also, I welcome all the dynamic participants for the second day of the international webinar series on carbon nanostructures and its applications. Yesterday, we had an excellent session and quite interesting session on the applications of carbon nanotubes as supercapacitors. Today, we are going to have a wonderful session on the development of various carbon nanostructures. With a short note, I would like to call upon Dr. P. Krishnan to introduce the speaker.
Thank you, sir. Hello, everyone, and welcome you all for this international webinar series. It gives me an immense pleasure to be a part of this webinar series as well as to give an introduction about the speaker. About the speaker, Dr. S. KISHORE, Assistant Professor, Faculty of Information and Communication Science, University of Information Science and Technology, Republic of North Macedonia. He obtained his bachelor degree in physics from Anonymanium Sundara University and master degree in material science from Anna University. And also he obtained his doctoral degree in the field of material science from Anna University. He did some short-term courses on machine learning from Stanford University and material data sciences and information from Georgia Institute of Technology. He started his research career as a project associate at IIT Madras under the guidance of Professor V. Subramanian, where he worked on the project entitled Synthesis and Characterization of Relaxer Ferroelectric Materials during 2005 to 2006. He has received several grants and honors in his career, like a Graduate Aptitude Test in Engineering in 2007, Junior Research Fellowship during 2006 to 8, Senior Research Fellowship during 2008 to 9, and Postdoc Fellowship during 2014 to 16. He has published several articles in highly reputed journals like Chemical Engineering Journal, Applied Surface Science, Journal of Nanoscience and Nanotechnology, RSA Advances, Material Research Expresses, etc. Also, he presented his research findings in several national and international conferences. He has participated in 2 national scientific projects sponsored by DRDO in IIT Madras, entitled Development of Passive and Illuminated Imaging System at 94 GHz under the Principal Investigator Professor V. Subramanian. And another project sponsored by DST entitled Synthesis and Characterization of Carbon Nanotubes using mesoporous MCM41 molecular saves, its application for memory devices in supercomputers under the Principal Investigator Professor A. Pandurangan from Anna University. Furthermore, he has filed a patent in his name for novel catalyst-free method for production of carbon silicon germanium and silicon germanium nanotubes by CVD method. With this short introduction, let me hand over the session to the speaker. Thank you, sir.
Thank you, Professor Krishna, for the nice introduction about me. So, very good morning to all my dear friends and colleagues. And I take this opportunity. I am very much privileged to be a part of this webinar, international webinar on carbon nanostructures. And I feel delighted, and I express my thanks to the team members of St. Joseph College of Engineering for providing this platform. And it's my real pleasure in sharing my research experience with my friends and my colleagues who are present here for this today's meeting. Okay, so coming to the presentation. Am I audible to everyone?
Fine, sir. A little more louder, sir.
Okay, fine.
Okay, sir.
So my topic, the topic that is given to me for today's presentation is about development of various carbon nanostructures. And I take this title because this is one of the part of my research career, where I did my PhD in the field of carbon nanotubes. So this is the reason why I took this topic. So currently I work in St. Paul the Apostle, the University of Information Science and Technology, North Macedonia. Okay, so you can see here where this place basically is located. So you can see the place over here. Okay, so the Macedonia is a small country that you can see, which comes in the part of Europe. It's surrounded by Italy here, Greece over here, and then Bulgaria, Serbia. So these are some of the places that you can see surrounding this, and we are very close to Greece here. So I am currently working here in this place, North Macedonia. Okay, so this place is a little bit unknown to most of the people, but this is one of the beautiful places that you can see if you come to Europe. Okay, so it has some beautiful landscapes here. It has beautiful winter. It has a beautiful summer and beautiful spring. You will definitely enjoy this place if you are coming to this place. Okay, so this is the university, which is located in Ohrid in Macedonia. So here is the here I work since 2016. Okay. So this university is mainly focusing on information technology, basically for computer science background. So this is a platform, this is a place where you can explore more in the field of computer science and technology. And coming to the main presentation, today I would like to share with you a few experience about my research in carbon. This presentation is mainly focusing on giving you a nutshell of the results or some interesting results that I have come across in my research career. Okay, so like the title says, it's about nanostructures, carbon nanostructures. So this presentation will have a small introduction about carbon, and then it will include carbon nanotubes. It will include carbon nanospheres and the carbon nanosheets. Then we have carbon nanodots. Then we have carbon, which is doped with various heteroatoms, foreign atoms. And I will talk a bit on the application, and then we will conclude this. So this is the main portfolio or main agenda of this talk. Okay, so I will be talking mostly on my research and my experience, and so it will be easy for me to explain you from my experience. Okay, so this is one of the most beautiful element that you can see in the periodic table, that is carbon. Okay, so the carbon is taking the position of in the 14th period of our periodic table. It has an atomic number. It has an atomic number 6, and it has an atomic weight of 12. And this is represented by letter C. Okay, so this is one of the beautiful element that you can see in the universe. Even I can say that it's one of the fifth. I can say it's the 15th most abundant material that you can see on the Earth crust. Okay, so every predominantly most of the elements or most of the compounds or most of the materials that you come across will have a carbon content. Okay, so without carbon, there is no material that you can see in our day-to-day life. You come across a lot of materials in carbon. So we have different types of carbon. We have different forms of carbon. We are daily coming across. We are daily crossing these materials which has a carbon element. Okay, so when we go a little bit technical into the material side, we will mostly talk about carbon materials. This material is a really interesting material. The the reason why it is more interesting is that it has the capacity, or it has the capability to take different dimensions. Okay, so here in this slide, you can see that you can see this carbon is having different dimensions, like 0 dimension, 1 dimension, 2 dimension, and a 3 dimension. So when it is in the form of 0 dimension, you can see that this has a name of a fullerene. You know, fullerene is a 0 dimensional material that is first discovered in the year 1985. So it's nothing but it's a molecule of carbon which we call C60. So this is a 0 dimensional material because it doesn't have any x-axis or y-axis or z-axis anymore here. So we call this 0 dimension material, and this material was discovered in 1985. And we are more attracted to this field of carbon because of this discovery made in 1985. 85. And also the main reason is that it was awarded a Nobel Prize in the year 1996 in the field of chemistry for this fascinating discovery. Then we have one-dimensional materials, one-dimensional material with one axis materials. So we call that carbon nanotubes. They have a tubular structure, and you can see carbon molecules in the benzene molecules attached to them. You know, they encompass of all these carbon molecules here. And they are one-dimensional, and this is discovered in the year 1991 by Ijima. And it has been a boom in the research field of material science after the discovery of carbon nanotubes. And recently we have 2D materials, which is called graphene. Graphene is nothing but a single layer of graphite, which has 2 dimensions here. Okay, so this is one of, again, a remarkable material that you can see since the discovery of carbon materials. So this is discovered in the year 2004, and it has it was awarded Nobel Prize in the year, I think, 2010. So this is a 2-dimensional material which is dominating the material science. You cannot see any research without graphene nowadays because it has a high mobility and it has a high electrical conductivity, and that makes this material more beautiful and effective. And then we have a new material which is called, which is a 3-dimensional material. It's a carbon, and we call that Mackie crystal. So currently there are research going on this material. The gist of this slide is that you can find the carbon materials in all dimensions, like 0, 1, 2, and 3. Okay, so they have different applications, and that makes these materials more special. Okay, so I will talk a little bit on carbon nanotubes. We have come across the term carbon nanotubes in most of the research, and the concept or the phenomena that is behind the formation of this carbon nanotube is shown in this diagram. You can see you have a substrate, and the substrate has a metal catalyst over that. Okay, so this is one of the most important things that you need before going for a synthesis of carbon nanotubes, because this is going to act like the seed, or like you grow a plant, you have a seed. So this metal catalyst is going to be act like a seed, and you have carbon sources coming here, and the reaction between this metal catalyst and this carbon source is going to give you a carbon nanotubes or carbon nanostructures. Okay, so this metals plays an important role like a catalyst for the formation of carbon nanotubes. So for this purpose, we have different techniques like chemical vapor deposition, where you send the carbon source and they get dissociated or they get splitted, and they fall on this, they diffuse into these metal particles, and then they grow like a carbon nanotubes. Okay. So basically, we have 2 different techniques for the growth of carbon nanotubes. This is the representation of the basic growth. So we call this as a tip growth mechanism and a base growth mechanism. So the concept is same like we explained in our previous slide. You have a metal catalyst and you have a carbon source. And during the reaction, what happens is that these metal particles pull to the tip. They go to the tip. So when you find a metal particles on the tip, you can say that it's a tip dog method. In contrast, you can see the second scenario where you can see this same process happening, but the metal particle stays on the substrate and the tube protrudes outside. So the tube comes outside, okay, after crystallization. Okay, so when the catalyst is attached to the substrate, we can call that as a base growth. It's similar to the plant growing from the ground. Okay, so these are the main technical point or the mechanism that you can see in the growth of carbon nanotubes or any structures where you need a metal catalyst. And there are different techniques for synthesis of this material. The techniques includes arc discharge, laser ablation, and chemical vapor deposition. Okay, so these are the most common techniques that are being used for the synthesis of carbon nanostructures or carbon nanotubes or carbon materials. So each method has its pros and cons and advantages and disadvantages. And if you go for industrialization or if you go for a mass production of carbon nanotubes, and you have to go for chemical vapor deposition. Chemical vapor deposition is considered more advantageous, or it has been proved to be more advantageous compared to these two techniques. So we go with chemical vapor deposition because it's a very simple and a very economical technique. And if you do a reaction in this, you will have an enormous amount of quantity, or you have product in a huge quantity and more purity. And this is one of the best methods that can be used to control the structure of the carbon nanotubes or any carbon materials. And you have the possibilities of controlling the parameters for engineering or for designing the carbon nanostructures. So we choose carbon nano, we choose chemical vapor deposition for the purpose of synthesizing carbon nanotubes or any structures. Okay, so now after concluding the introduction, I am just jumping to my research and my experience in various topic on carbon. This is a work that has been done for the synthesis of carbon nanotubes using a cobalt catalyst. The innovative part of this paper is about this deposition, which is called electrophoretic deposition. So electrophoretic deposition of cobalt catalyst layer over the stainless steel. We use this as the substrate and this as cobalt as a catalyst, and this method for the preparation of the catalyst. And we use chemical vapor deposition for carbon nanotube synthesis. Okay, so this is what you see here in this concept of electrophoretic deposition. So here in electrophoretic deposition is one of the simple methods that you can prepare a catalyst for the synthesis of carbon nanotubes. For this purpose, you just need a cell where you have a beaker with electrolytes. For example, you have a cobalt nitrate inside this, and then you have two plates, which is basically a stainless steel, and you have a DC power connected to this. So when you switch on this DC power, what happens is that this electrolyte, which is supposed to be the your cobalt nitrate here, it get dissociated into two ions we can call cobalt ions and nitrate ions. So this charge which is present in the ions, cobalt has a positive charge and nitrate has a negative charge. So this is what that motivated us to create a cobalt catalyst layer over this one. So this positive charge get attracted to the negative terminal, and the negative ions get attracted towards the positive terminal. So we were successful in producing cobalt layer, a pure cobalt layer of the stainless steel. Okay, so this layer is subjected to calcination or annealing at 500 degrees centigrade, where you can see this film is split into small nanoparticles, it's small islands or small particles. So this is what we need for carbon nanotube synthesis. And when we subject this for a chemical vapor deposition process, we can see the output with carbon nanotubes going on this substrate. The beauty of this experiment is that you get two types of carbon nanotubes. One type of carbon nanotubes coming from this cobalt particles, nanoparticles. Sorry. And the other one is from this stainless steel. Stainless steel, you have a bulk carbon nanotubes. Okay, so it was a very interesting research for doing for extracting the most crystalline carbon nanotubes. So here in this same picture, you can see the different morphologies of carbon nanotubes, which is extracted from, which is done using this technique. So this is a portion of a cross-sectional view of this stainless steel, which has carbon nanotubes from cobalt and from stainless steel. Okay, so this gives you the picture of cobalt nanotubes obtained from cobalt nanoparticles, and this is the carbon nanotubes that you get from bare stainless steel. So this picture, this image will show you the more clear view of this carbon nanotubes. So this image shows cobalt carbon nanotubes from cobalt coated stainless steel, and this shows a bare stainless steel. So you can see the difference between the structure. You know, the structure is having a variation because of this cobalt and because of this without a cobalt. So this with the cobalt has a very beautiful multi-wall structure, and this is one of common morphology that you can find when you try to synthesize a carbon nanotube. So here you can see carbon nanotube, but it is having a lot of effects in that. Okay, so we try to do this optimization by undergoing various temperature reactions. So we have reactions going on at 700, 800, and 900. So you can see the changes happening with the structure of carbon nanotubes. So we have thin and we have thick and we have more thicker carbon nanotubes at different temperatures. And this is the TEM image, which shows again different morphologies of carbon nanotubes, multiple carbon nanotubes at the different temperatures. So you can see that when we increase the temperature, the thickness decreases, and there are few amorphous carbon deposited over this. Okay, so here in this image, you can see the optimization done with respect to the flow. I mean, you have a precursor for preparing carbon nanotubes, the carbon source. So here we use acetylene for the synthesis of carbon nanotubes. So we optimize this reaction with respect to the flow rate of acetylene and hydrogen, which is going to be the carrier. So you can see the variations of different carbon structures at different flow rate or different ratio of these gases, 0, 10, 25, 25, 40, 10. So when you try to mix these gases, you can find variations in structure. Okay, so here we will get an idea about the elements which is present in this in the product. So we take the index of CNTs grown over cobalt stainless steel, and this is a proof that you have a carbon, you have a cobalt, you have iron coming from the stainless steel. So this is an index picture confirming the elements present in the product. Okay. So then you have an Raman spectroscopy here. Raman spectroscopy will give you a perfect understanding about the crystallinity of the material. Your material can be amorphous or it can be a crystalline material. So if you look into this Raman spectroscopy, you can see two bands coming out of this. One is a D band and a G band. And this G band indicates the graphitic structure, graphitic carbon around 1,500 and 1,600. And you have a D band, which means you have some defects in your carbon that is coming around 1,300 and between 1,200 and 1,400. This peak. So this peak indicates the presence of both graphite, we have a dominating graphitic structure, and we have few amorphous carbon in our product. Then coming to the next work which was done on CVD for the synthesis of Y-shaped carbon nanotubes. So we are successful in creating a Y-shaped carbon nanotube in the CVD method. So here the 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 catalyst is one of the most novel component of this research. We take iron doped or iron loaded aluminum phosphate catalyst. So this is the this catalyst provides the um, provides an what do you say? It is responsible for creating this Y-shaped carbon. Okay. So here I can show you this XID picture, which show XID images of uh, the catalyst. This catalyst, which is called aluminum phosphate, is one of the it's a very a good material, catalyst material, which is commonly used in catalytic reactions. So this is an amorphous material. Basically, this is an amorphous material. You can see the amorphous nature of this material with this peak, a broad peak in the XRD, okay, in this region, representing an amorphous nature of aluminum phosphide. So this material, when loaded with iron, it has a good dispersion of iron. Like here, you can see the image of dispersed iron, aluminum phosphate. So they have the capacity to include iron nanoparticles, which are going to be the catalyst for our carbon nanotube synthesis. Okay, so this the XID will give you the difference between unloaded aluminum phosphate and loaded aluminum phosphate with iron. And this is the characterization, which is called XPS. X-ray photoelectron spectroscopy, and this characterization is an authentic tool to confirm the presence of elements that is present in the catalyst or any material. So we can find the binding energy. With respect to the binding energy, we can understand the constituent elements present in that material. So here, the presence of aluminum is confirmed from this formation of binding energy in this region. And then we have phosphate with the 2p2 orbitals, and that is confirmed from this peak around 132. And then we have oxygen, which is present in abundantly in the environment and in the material. And then we have iron, which is being doped with this catalyst. Okay, so these peaks will confirm this presence here. Then when we try to do the experiment after CVD, you can confirm the formation of carbon nanotubes with respect to the study with XID. Here, this XID will give you a proof that you can create carbon nanotubes over this catalyst. So this black spectrum represents the carbon nanotube with catalyst. Okay, so this has the combination of both the carbon peaks, which indicates 002 plane and 100 plane of carbon, in addition to the catalyst and a catalyst peak of iron. So when we, after purification, when you try to remove this aluminum phosphate from this material, from this product, you end up with the final product, which is already carbon. So we can have we can extract carbon after acid purification. So this peak is a survey spectrum of XPS, which confirms all the elements that is present in this catalyst, which includes aluminum, phosphorus, carbon, oxygen, iron. And this is an UV spectra of the iron aluminum phosphate material that is being used for this synthesis. And you can see the bondings of this material here, functional groups. Then you can see from this SEM images the formation of Y-shaped carbon nanotubes. So we achieved this morphology of carbon nanotubes, which have a junction type or a Y-type junction. We call it Y-shaped carbon nanotubes. And this happens in this optimized condition of 3% of ion loading above this catalyst at a temperature of 700 degrees centigrade. So we can see more networks or more Y-shaped uh, morphologies happening here. So this is one of a good, interesting result that is obtained. And you can see the TEM image of Y-shaped carbon nanotubes in this. It, from this TEM image, you can see in the inside the walls of this Y-shaped carbon nanotubes, which has a crystalline carbon nanostructure. So we confirm that it has a multi-walled walls attached to that. Then you can understand the mechanism of formation of these Y-shaped carbon nanotubes using this catalyst. uh, we presume that our catalyst, aluminum phosphate, has iron nanoparticles over that, and in addition to that, it has some iron oxide nanoparticles. So we can find two types of species over this catalyst. So during the reaction, what happened is that you can see two nanoparticles between an oxide nanoparticles. So when you find some barrier between two nanoparticles, what happens is that you have two carbon nanotubes coming together, and they are creating a Y-shaped carbon nanotubes. So the diffusion of carbon atoms happens here, and this makes this common branch that makes them a Y-shaped morphology. So that's what we presume, and we predicted on this research. Like before, we have here Raman spectroscopy to study the crystallinity nature of this material, and you can see that from this picture, you can see the variation happening in the Raman spectroscopy before purification and after purification. So you can see in this Raman spectroscopy that defect is being dominated in both cases. You can see the defect. So the defect of this structure is being incorporated, or it has been happened because of the formation of the Y shape. So the Y shapes are created mainly because mainly due to the incorporation of various uh, disordered carbon. Okay, so we have disordered carbon dominating this material. So that's the reason why we find the ID by G ratio greater than 1 in both cases. Okay, so after purification, you can see that it has come to a small or a small value. So we can control the defect in the small amount by purification, but still we have the carbon defects in this, which is which is due to the Y-shaped carbon atoms. Okay. Then talking about the next work, here in this work, this is one of the most, it's an interesting work that has been done. We have used enriched carbon nitrate nanospheres, and we were able to create nitrogen doped carbon, which is a beautiful material that can be used for various applications here. So we have included, or we tried to create a heterostructure by combining this in the carbon nitrate with molybdenum sulfate sheets. So these two materials are put together, or they form a heterostructure for lithium-ion batteries applications, and that is the innovative part of this research. In this research, we were able to create end-doped carbon, or a graphitic carbon nitrate material with the help of a precursor which is called melamine. Melamine is a very good material that you can create a bulk carbon nitrate by calcinating it around 400 degrees centigrade. You get a bulk carbon, graphitic carbon, and then you can you go for ultrasonation method. Ultrasonation method helps you to extract these layers, and so this is a combination of both the calcination and ultrasonation, which will give you this exfoliated graphitic carbon nitrate nanosheets. So this helps you to get carbon nitrate nanosheets. Um, Here, in this XID pattern, you can see the peaks connected with graphitic carbon nitrate, and you have this peak represents molybdenum sulfide, and this is the heterostructure of two materials, which has a good compatibility between each other. So this confirms the possibilities of heterostructure between two layered materials here. So, so this is what we are more interested in. So here for this talk, we have a graphitic carbon nitrate because this nitrogen is being incorporated into this, and it has this exciting graph. Okay. Then this STEM images indicates the formation of sheets, which we call carbon nano sheets, carbon nitrate nano sheets with a layered structure. So this is a good indication of the morphology of nano sheets that has been occurred after. Um, I mean, this is about the pristine graphite carbon nitrate, and this is after uh, depositing the molybdenum sulfide. Okay, so this is TEM and HTEM of the material. When you try to make a heterostructure out of MOS2 and graphite carbon nitrate, you get this kind of a structure. It is one of interesting structure that is being used for this application of lithium-ion batteries. So here you can see this carbon nitrate spheres. It forms a spherical shape, and then you have a moisture coated over that. Okay, so this is confirmed from the HR term based on the interlayer spacing of 0.33 nanometers, which indicates the spacing of graphite carbon nitrate. And then you have confirmations from the moisture material from the interplanar distance, which is 0.623 nanometers with for the plane 002. Okay, so this is a beautiful observation that we get. And then we have XPS. XPS will definitely tell you the components present in this material. So it conforms carbon and then nitrogen. You have different carbon with different uh, this is what do you say? You have different bondings of carbon, nitrogen to the carbon. So it is indicated by three spectrum. You can split them into three. So it indicates different type of bondings at different binding energies. Then you have sulfur attached to this material, which comes from molybdenum sulfide with the two different bondings. And then you have molybdenum with two different bondings here. Okay, so this gives you an overall picture about the components or chemical constituents present in the material. Then in this research, we have investigated the possibilities of formation of carbon nanospheres using a simple catalyst, which is nothing but a sodium chloride crystal. So common salt we call it. So we use the same chemical vapor deposition method here for the formation of solid and hollow carbon nanospheres. So this is one of it's an interesting research because it's very cheap and very economical and very simple. So talking about this, here we have an exciting image of the the product that we obtained at different temperatures like 500, 600, and 700. So you can see the variation happening with the peaks, intensity of the peaks with respect to the temperature. So there's a increase in this peak of 002, and this is we can see this peak of 100 originating at different temperatures. Okay, so when we increase the temperature, you can see temperature, this peak is basically decreasing. Okay, so the reason for this will be explained in the next slides. Okay, so we have three different morphologies coming in three different temperatures. If you look for 500 degrees centigrade, you can see this. You can see a sheet-like structure of carbon or flake-like structure of carbon coming from 500 degrees centigrade. Then at 700 degrees centigrade, you can see a change in the radiation happening here. You can see they are converting into, it's a transition happening from the sheet to a sphere. And then you can see some hollow structures here in some, you can see an opening over here in temperature of 600 degrees centigrade. And then you come to the 700 degrees centigrade, you will see perfectly a solid sphere without any hollow structures. So the variation of this structure is being studied at different temperatures. And for better confirmation or clarity, we can see this TEM images. Here you can see at just 500 degrees centigrade, you have sheets with the graphitic walls. And then you have hollow structures at 600 degrees centigrade. And again, if you examine the walls, you have graphitic walls here. And then you go for the 700 degrees centigrade higher temperature, you can get a solid sphere over here with the walls which are not crystalline, or they are disordered when you go for higher temperatures. So again, with a better understanding from this STEM images, you can see a sheet formation happening at the lower temperature, and then you have a hollow sphere coming in 600 degrees centigrade, and then you have a solid sphere coming in the higher temperature of 700 degrees centigrade. And the corresponding SGAED pattern is given for each structures. Okay. So here you can see the mechanism behind the formation of carbon nanospheres. Now to explain this carbon nanosphere formation, it's very interesting to observe this structure. So we assume that we predict that we have a carbon structure, we have a crystal of sodium chloride. So what happened is that during the reaction of depositing of carbon, we have a uniform deposition happening at 500 degrees centigrade. Okay, so at a lower temperature, this crystal is covered entirely with these carbon molecules, and when you try to wash away this sodium chloride, you get sheets out of that. Okay, so in the second phase, when you come to 600 degrees centigrade, what's happening to this transformation is that the sheets that is formed over sodium chloride is not thermally stable. Basically, they have the tendency to come to a stable condition at higher temperature by transforming into spheres. So due to that reason, you can see that in order to occur a equilibrium in the structure, they start rolling to structures. They form hollow structures here at 600 degrees centigrade. And again, you start increasing the temperature. You can see this temperature will give you a solid sphere, because it attains a saturation by reaching a temperature of 700 degrees centigrade, where it creates spheres. So we don't use any catalyst over here for the catalyst for synthesis of carbon nanospheres. So it's basically based on the transformation of, or the stability of the material at different temperatures that creates the different morphologies like nanosheets and hollow nanosheets, hollow nanospheres and solid nanospheres. Okay. So when we study the Raman spectroscopy for the crystalline nature, we can see that at different temperature, you can see the ID by J ratio is changing. So lower temperature has a 0.83 ID by J ratio, and then 600 gives you 0.95, and okay, 600 gives you 0.71, and the 700 gives you 0.95. So you can see that you have more defects happening at higher temperature. Higher temperature gives you more defects because of deposition of amorphous carbon over these nanospheres. Okay. When we talk about the application point of view of these materials, this work is really interesting, because we created a material. We investigated carbon nanotubes, composites with a polymer, which is a polyvinyl alcohol, for the application towards non-volatile memory devices. Okay, so it is a device for storage of memory, storage of charges, or storage of data. So we work on this material with the help of carbon nanotubes. So carbon nanotubes has an important role to play in the memory storage applications because it has the capacity to hold the electrons because of its one-dimensional structure. So it acts as a perfect channel for the flow of electrons, and it can accommodate electrons at different conditions. Okay. The reason for using polyvinyl alcohol in this research is that, so here you can see we have a polyvinyl alcohol which is being used for creating a memory devices, fabricate a memory device. Here you can see this polyvinyl alcohol has a remarkable or excellent property of combining with carbon nanotubes, and they are uniformly disposed. Carbon nanotubes can be uniformly disposed in polyvinyl alcohol. Normally, carbon nanotubes has a disadvantage of dispersion. They don't have a uniform dispersion with all the solvents or any other solid liquid mediums. So we go for functionalization of carbon nanotubes normally. But in this case, you don't go for any functionalization. You directly go to this polymer because it has the capacity. This polymer, polyvinyl alcohol, has the capacity to disperse the carbon nanotube more uniformly, which is more essential for fabrications. When you try to create a thin films, you need a good dispersion of carbon nanotubes. So for that reason, we have a PVA dispersed with the carbon nanotubes. So we have two different type of structures. One is called MOF structure, and then it's called MIM structure, metal insulator metal structure. And you have different studies going on with this memory capacities due to the carbon nanotubes. Okay. So for this purpose, we use carbon nanotubes, which has grown from nickel coated stainless steel, like we mentioned in our previous research. Here we use a nickel catalyst to grow carbon nanotubes with a good length and more dispersion. And this is an EDAX spectrum indicating the presence of nickel, oxygen, iron, and carbon. Here, this is a good, representation of a dispersion of carbon nanotubes wrapped with polyvinyl alcohol. So this gives you a good understanding about how this polymer is being dispersed in the individual walls of this carbon nanotube. So here you can see the coating of PVA. Then we go for TEM images to study to confirm that coating has happened in a uniform way. So you can see this coating of individual carbon nanotubes wrapped with the polyvinyl alcohol happening in a very tremendous way. Okay, so here in this research followed by this research, we study in detail about the resistive switching memory characteristic of memory devices in this work. So here in this investigation, we use carbon nanotubes with PVA to study the resistive memory device capacities. Okay, so we get carbon nanotubes from stainless steel coated catalyst layers of nickel and then iron. So here we make a comparison between carbon nanotubes drawn from iron catalyst and a nickel catalyst. So we can find a difference between these two catalysts. There is a change in morphology of the quality and the quantity of the carbon nanotubes that is being coming out of this different catalyst. So we get a good quantity and a good quality of carbon nanotubes, multi-wall carbon nanotubes from iron catalyst. And we choose this for further studies. And this is a system image which gives you a clear picture about the material quality. So we have long tubes coming from this iron catalyst. So we have a long, maybe millimeter long carbon nanotubes, which is very basically necessary for device fabrications. So we have long tubes coming from this catalyst. So here, when we go for uh, so you can see the difference between these two types of materials. Okay. Here, we were trying to make single wall carbon nanotubes. So for the purpose of carbon nanotubes, there are two types of carbon nanotubes, multi-walled and single wall. So previously we were coming across multi-wall, but we were trying to find some single wall carbon nanotubes, which has more conducting properties than um, multi-wall carbon nanotubes. So we go for a catalyst, which is called a nickel dot aluminum phosphate catalyst. So we are trying this catalyst. So this is the XID pattern of the catalyst with the various loading, and you can see the formation of amorphous aluminum phosphate, and then you can see that doping of nickel oxide over this catalyst in presence of these peaks over here. Okay, so this confirms the presence of formation of nickel aluminum phosphate catalyst, and this XPS will give you the confirmation about the components present in the catalyst, like nickel, aluminum, phosphorus, and oxygen. And this is the optimization study that has been done at different temperature, like 600, 700, and 800. And we can see that there are some formation of carbon tubes. So here, creating a single wall carbon nanotube mainly depends on the size of the nanoparticles that has been deposited, and the temperature and the flow rate of the reaction, flow rate and the reaction duration that you're going to have. So this is another optimization with respect to the time. You can see at different time, you can see the changes happening with the size of this carbon nanotubes. So we can see more thin, more delicate, and more thin structures happening in 15 minutes of reaction. And again, going with the different optimization of the both hydrogen and acetylene flow, you can see again an optimization happening here, and around this ratio 72, 75 to 25 flow rate, you get a good structure of single wall carbon nanotubes. So again, studying with different percentage of loading of nickel, because nickel is very important for this synthesis of single wall carbon nanotubes. So you can see that with the 3% of loading, we were able to get the minimum dimension or minimum size of carbon nanotubes. So XID, Raman spectroscopy will confirm the presence of single wall carbon nanotubes. Apart from D band and G band, which is a common band that is being generated in most of the carbon materials. But here, when you come for a single wall carbon nanotube, you see a extra peak over here. It's called radial breathing mode, and this represents the single wall carbon nanotubes. And this is the TEM images showing you the formation of single wall carbon nanotubes coming from a nickel catalyst. And this follows a bottom growth mechanism of carbon nanotubes here. So it is very long, and then it has the diameter of few nanometers. Okay. Then coming to the next morphology of so we are interested in creating more morphologies in carbon nanotubes. So create a different morphology, we had to go for a different catalyst, and this time we are going for a catalyst which is called an MCM41. This is a mesoporous material. Mesoporous materials which has a different pore structures in the very in the range of nanometer scale. You can see these pores in this MCM41 materials, and these pores will help you to create beautiful structures of carbon nanotubes. So this is the SEM image of iron doped MCM41, and this is the um, what do you say? This is with iron MCM41, and this is having an element which is called tin, which has been added to this to create some beautiful structures. So here we use tin iron MCM41, and this is the picture of MCM without loading and an MCM material with loading. So you can see the metal nanoparticles dispersed over this catalyst in comparison to this. Okay. So trying to study this CVD growth of carbon nanotubes, you can see some different structures coming, beautiful structures coming out of this catalyst. So you can see a spiral shape of carbon nanotubes in this structure, which happens at a temperature, at a reaction duration of 10 minutes. And you can see more spirals happening in these structures. So we were able to come across more beautiful structures coming, this combination of spiral or spring-like or a linear. Okay. So we have a lot of beautiful structures coming at different flow rates. And this we take to explain that we can create a coil-shaped carbon nanotubes out of this catalyst, which is called tin iron combination in a MCM41. So you get spherical carbon nanotubes here. So this enlarged version of this adjoint figures, I mean pictures, gives you a good understanding about the layers, graphitic layers that has been present on the walls of this material. So this is a beautiful structure. Then these materials, carbon nanotubes, has the capacity to have form composites. They are very good material for mechanical properties. For that, we can create a lot of composites out of this. So we tried aluminum phosphate in combination with carbon nanotubes. So we can see the coating of aluminum phosphate with the carbon nanotubes. It has a uniform coating. And then we tried with silicon dioxide in these two cases. So again, it has a good adhesion of silicon dioxide coating over carbon nanotubes. So aluminum phosphate and the silicon dioxide are very good fillers that have been used for mechanical properties of material, to enhance the mechanical properties of the materials. So here we have the combination of aluminum phosphate and the CND, and then we have silicon dioxide and the CND. Okay, so this gives you the temperature of this A and C. These two images will show the silicon dioxide coated CNDs, and this picture B and D will show the aluminum phosphate coated carbon nanotubes. So the concept is that it has carbon nanotubes is a very good candidate for a composite applications. So this is the composite material, the same images of the composite material. So you can see a neat epoxy composite over here. Then you can see a neat epoxy filled with carbon nanotubes along. And this image will show the aluminum phosphate coated carbon nanotubes filled nanocomposites. And this shows the silicon dioxide coated carbon nanotubes embedded epoxy composites. So you can see the variations happening with the different loadings. So this study has proved that aluminum phosphate CNDs has a good mechanical strength and thermal stability. And talking about a few findings from my Indian patent that has been filed based on the material. So we were trying to create a material without a catalyst. So it is a novel catalyst-free method for the production of carbon silicon germanium and silicon germanium nanotubes by CVD. So the novelty of this pattern is that normally silicon forms wires, silicon and germanium forms wires. But in this case, we are getting a nanotube structure where you can dope silicon, germanium, and the carbon in one tube. Here we have silicon and germanium. And one more advantage of this pattern is that we don't use a catalyst for this for the fabric or for synthesis of these materials. Okay, So this is the image. You can see that is formed at 800 degrees centigrade. This is a silicon, carbon, silicon, germanium nanotubes that you can see, which forms in a huge quantity. Okay, it gives a good yield. And this is the TEM image, which clearly indicates that it forms a long tubes, and it has a hollow structure, which is one of the remarkable findings. We don't have a tube formation in silicon nano silicon materials. So this is a good achievement that we can take the credit because of the incorporation of silicon and germanium and carbon. You can find three elements in one tube. So this is a beauty of this material. So to confirm this presence of these materials, we can see the carbon, germanium, and silicon from the Iraq spectrum. Okay, so it clearly indicates that it has three components in this. And then you have the Raman spectrum confirming the presence of carbon and silicon and germanium due to their vibrations. Okay, and this picture in this is the same images of silicon germanium nanotubes. You can see a millimeters long nanotubes formed out of silicon germanium, and they are of good quality. So it's a long tube. It's a long tubular structure with components of silicon and germanium present in this tube. So we achieve this by changing the ratio of the precursor that is being used, silicon or germanium. So we use a liquid precursor over here, and we are trying to change the ratio of the liquid precursor of silicon and germanium to get the structure. And last but not the least, so the recent publication that I get about, so we were working on this material. So I was interested in knowing about carbon nanodots, and we were able to create carbon nanodots in this work using our common tender coconut water, and we were getting it very beautiful carbon nanodots out of this source, which is a natural source. So it's a green synthesis of carbon nanodots using an acid-assisted ultrasonication route. So it's a combination of both acid and ultrasonication. So here you can see, for a better understanding, we use coconut water, and we mix it with sulfuric acid, and we go for ultrasonication at a temperature of 70 degrees centigrade, which gives you a carbon nanodots. We get carbon nanodots out of this coconut water due to the reason that you have starch content in the coconut water, which acts as the precursor for carbon, and then you have sulfuric acid, which react with this coconut water to extract the which acts as a catalyst for the formation of carbon nanodots. Okay. So this is the exciting pattern that you can see for carbon nanodots. You have amorphous structure basically for carbon nanodots. So this indicates this is the 10 images you can see for carbon nanodots, which are uniformly disposed and with a few nanometer size of 1 to 4 nanometers in average. Okay, so here you can see the graphitic layer of carbon, indicating the carbon in the interplanar structure. Okay, and then you have applications for carbon nanodots with a good fluorescent properties. So it emits a green fluorescent light. Okay, in this region. So this is a PL spectrum indicating the emission of a green light. Okay, so in this range you can get a green light. When talking about the application point of view, carbon nanotubes are good candidate for memory devices. So here you can see the characterization of memory devices, which is a capacitance voltage study for a material where different doping of carbon nanotubes. So you can see this window, which is the potential window, increasing with the increase of the content of carbon nanotubes in the device. So it gives an information that the carbon nanotubes has the capacity to store more charge, and they can store more data. So this loading of maybe 1% of loading of carbon nanotubes give the maximum storage without any leakage of current. And then you can take it to the next structure, which is an MIM structure, where you can see a transition of high conductivity to low conductivity, where there's a change of resistivity happening. So you can switch from one state to another state. So this is called a bistable electrical switching device, memory device, which is accomplished with the help of 3% loading of carbon nanotubes. So it's a very good material for memory applications. Then this carbon nanotubes, or I mean the graphitic carbon that we have created before with MOS2 has given a tremendous performance in the application of lithium-ion batteries with a good discharge capacity greater than 2000, when compared to MOS2. So this is going to be MOS2, and this graphitic carbon MOS2 structure gives you a more capacity because of presence of graphitic carbon and nitride. Then when we go with the application for carbon nanospheres, you can see that the charge discharge cycle for battery applications with using a carbon nanosphere electrodes, you can see a good capacity has been achieved, which is greater than the graphite. Coming to the summary, I will wind up here with the summary of the findings that we have seen. So EPD, which is the electrophoretic deposition technique, is considered to be a simple tool to create multiple carbon nanotubes using various layers, various catalysts like cobalt, nickel, and iron over stainless steel. And then we have a carbon nanotube disposed with PVA, and we can take PVA as a good candidate for dispersion of carbon nanotube for more applications in memory devices. And in the case of creating this, when we try to create this the memory device structure, we were able to create. We can get a good memory characteristics by storing a good amount of charge at the around 1.9. And then you have applications of carbon nanotubes in a MIM structure using 3% of carbon nanotubes, where it gives a high state of current ratio of 10 power 7 at a low voltage of -1 volt. Then we have a catalyst which is called iron loaded aluminum phosphate, which is a good candidate for creating Y-shaped carbon nanotubes and single wall carbon nanotubes. Then this material, the heterostructure of carbon nanotubes, carbon nitride and MOS2 are a good candidate for battery application, which gives a specific capacity of 857 milliamps per grams after undergoing more cycle, 50 charge discharge cycles. And then we have nanospheres, a good candidate for lithium-ion batteries, which gives a charge capacity and higher charge capacity, which is greater than the graphite. Then we have the novel material, carbon silicon germanium and silicon germanium nanotubes, which find with an extraordinary structure of tubular structure for various applications. Then you can create carbon nanodots using carbon like coconut water, and we were able to get a green fluorescence in this carbon nanodots with an excitation of 5-10 nanometer. Thank you very much for your kind attention, and so
thank you, sir.
Yeah.
Yeah, sir. Now we can stop sharing and come to this window so that you can answer the questions. Yeah, I'll post one by one, sir. You kindly see the window and answer the questions.
Okay.
Some of the questions. Is it possible to get CNT by electrophoretic but electrodeposition without further CVD technique?
Yes, actually, the process of creating carbon nanotube is basically happening because of decomposition of a carbon source. So electrophoretic deposition will only give you coating, coating of a catalyst. It doesn't form carbon nanotubes there. So it's basically not practically possible with this process. So we had to go for we had to go for high temperature reactions chemical vapor depositions and other techniques. So we need a high temperature for creating carbon nanotube. Electrophoretic deposition or electrodeposition does not guarantee a formation of carbon nanotubes. We had
Thanks.
to, yeah,
Thanks.
we have developed any shape of carbon nanotubes or selectively. It's a
Yeah, the
question.
question seems to be incomplete. So shall I close the next question?
Uh-huh. Why carbon doesn't have any structure below 500 degrees centigrade? Yeah.
I think
So he's asking why carbon doesn't have
proper
any
structure. I
structure.
think, for example, you said that at 700 degrees Celsius,
Uh-huh.
it has a
Uh-huh.
spherical shape, but why
Yeah,
it doesn't
yeah.
have a proper structure at lower temperature? I
Yeah,
think
the
the question
answer for
seems to
this
be.
question is because if you are going for carbon nanotubes with a graphitic structure, because we know that we need we look for a graphite, a graphitization or the crystallinity of the material. To get more crystalline material, we go for high temperature basically. So this is happening in the higher temperature. When higher temperature, we have a dissociation of the precursor, which is the carbon molecules. They get dissociated more freely at a temperature above 500. So you have the deposit, you have the chances of getting crystalline materials above 500 degrees centigrade. If you are going below 500 degrees centigrade, what happens is that you get carbon structures, but they are going to be amorphous. Amorphous means
Right.
you are going to get some coating over that. So that is going to destroy your structure and you don't get the expected result or the structure that you want. So
Thanks.
that's the reason why you don't go for low temperature basically.
Next question.
Yes. Role of tin. Yeah, the answer is about the catalyst or the material. I mean, the nanoparticle that is being used. Tin has melting temperature. If you look for the melting temperature of both the tin and iron, you can see that the tin has a low melting point. So this is going to influence the formation of carbon nano coils in this case. So it is the melting temperature of these nanoparticles. So that is the reason why we go for tin. Yeah,
You're fine, sir. So
yeah.
I think the question session is completed. One more question, the last question.
Uh,
This will be the last question, I think so.
so can CND
May-
be made hydrophobic? Basically, carbon nanotubes are hydrophobic actually. So that's a real nature of carbon nanotubes. They are hydrophobic. They are not going to get dissolved in in water. You don't dissolve carbon nanotubes in water. It's going to float on when you put it in the water. So it's basically hydrophobic actually. I don't say it's hydrophilic.
All
So
right, sir.
that's the real nature of CNDs. Yeah.
You're fine, sir.
Okay.
Just a moment. Yeah, it's a time for a word of thanks. Uh, Gratitude is a way of appreciation. Hence, I would like to thank respected Chairman Dr. B. Manoharan for providing this platform. Our Managing Director, Mrs. S. Jessica ma'am, Director Mr. B. Shashishekar, and Principal Dr. Vadi Shashikar Rao, Dean Research Dr. P. Parvadavardhani, and our Head of the Department and Convener Dr. V. Nandini Devi. Most importantly, I would like to thank the invited speaker, Dr. S. Chandra Kishore, who readily accepted our invitation despite of his busy schedule. It was really a wonderful session, sir. Today we learned the different methods of synthesizing carbon nanostructures. More than 400 participants benefited from your live speech. In addition, the recorded version surely will enrich more people without any doubt. Also, I would like to extend my deepest gratitude to all the participants for their interest to attend the webinar and made this a grand success. Thank you. Dear participant, you will receive the certificates within 3 working days, and kindly fill up the feedback form posted in the comment box. And also, we are going to conduct another webinar series. It is going to be okay. We are going to conduct that during this Friday and Saturday, 24 and 25th of 24 and 25 of July. Okay. So I also posted the link for that. Kindly you post it. Yeah, fine. So with this note, I end this session now. Thank you very much.
Thank you. Thank you.